Imagine waking up in a completely dark place with no windows or doors. You have no way of knowing if you are on a spaceship accelerating through space or near some object with gravitational pull on the planet. There is nothing around you to grasp, and the ceiling is so low that you can't even jump. At some point, you might ask yourself a simple question: how much time has passed since you woke up? This is a question we often ponder after what seems like a quick nap, only to realize hours have flown by. But really think about this question for a moment. The main challenge here is figuring out how to tell time without any tools or indicators of its passage. If you're very attentive and creative, in the absence of a clock, you might use your heartbeat or even count your blinks to create a new way of measuring time. However, the moment you fall asleep, you'd lose track again and be left wondering how much time had passed. So, what's the best way to measure the passage of time in any situation? Let's explore this idea a bit more. We have different units of time that serve various purposes: years, days, decades, hours, seconds, centuries, milliseconds, fortnights, weeks, the list goes on. What these methods of measuring time have in common is their relationship with some kind of oscillation found in a world. For example, a year is marked each time the Earth completes a rotation around the Sun. A day is one full rotation of the Earth on its axis. And to get hours, we simply divide this period by 24. Months are defined as a number of days, with a month of 30 days being the Earth rotating 30 times. Thinking about these cycles can help ground our understanding of time, even in a situation as disorienting as waking up in a dark, enclosed space, whether using the steady beat of your pulse or the rhythm of your breath. Finding a natural cycle can be a comforting way to measure the passage of time. A second is perhaps the most curious measure of time, but it too is tied to a natural oscillation. Originally, a second was defined as a day divided into 86,400 parts, but today, the International System of Units defines it as 9,192,631,770 cycles of radiation from the transition between two energy levels of the cesium-133 atom. In other words, a second is just another oscillation found in nature. Scientists determine this value, and voila, we have the second. Our understanding of time is simply based on something repetitive in nature. We find an oscillation that repeats and measure time from it. I could even create my own unit of time, say by throwing a ball into the air and defining my second as the time it takes for the ball to fall back to the ground. So, what's the best way to measure time? Seconds, decades, milliseconds, hours, or perhaps my new unit of time? Of course, different situations call for different units. That's why we created various units in the first place. It doesn't make sense to measure how long it takes to bread to bake in years, just as it doesn't make sense to measure the age of the universe in seconds. Our concept of a second could change if we used a different element than cesium-133, or if we lived on a planet that rotates faster than Earth, or even in a planetary system where an orbit takes less than 365 days. The point is, our perception of time is directly linked to the place we live. Here on Earth, the position and rotation speed of our planet shaped how we define time. So when we think about time, it seems straightforward to measure. Even ancient civilizations define time in their own ways, albeit rudimentary to aid in agriculture and other activities. However, time isn't exactly what a clock measures. Remember, a clock simply counts the number of oscillations. So what is time? Let's dismiss the simplest idea that time is the duration between two events. This definition is weak, and we can understand why. One of the first people to provide a more precise definition of time was Hermann Minkowski. He described time as a dimension of the universe. Similar to how space is a dimension, in real life, we experience three spatial dimensions: width, height, and depth. Minkowski added that time is a fourth dimension. Although I might be stationary in space at this moment, I am constantly moving through time, advancing 1 second into the future every second. This concept was fundamental for Albert Einstein when he developed his theories of relativity, both special and general. These theories have been validated numerous times since their inception. The fascinating aspect of the theory of relativity is that it was one of the first time in physics that time was defined as a tangible entity, in this case, a dimension. Before relativity, time was merely the difference between two events. To illustrate this, let's consider classical physics and the speed of a car. I can determine the car's speed by measuring a distance x that I can see with my eyes and using time, perhaps as a number of times a dog blinks between 2 points. Even if I substitute these values into kinematic equations, classical physics still holds. Without needing a precise definition of time, I can literally use a dog's blinks as a measure. This is crucial because in classical physics, time is absolute. It is the same everywhere, so there was no need to worry about it. This applies to other areas of physics, such as electromagnetism and even quantum mechanics, where time can be seen as an external factor. However, relativity changed everything. In relativity, time is now a dimension of the universe. It's something concrete, and more than just something, it's a dimension. Just like space, the three dimensions of space can be directly experienced. When I hold a box, I can see its width, height, and depth. Additionally, I can move freely in space, forward, backward, right, left, up, and down. I can even return to the same spot I was in before, because space doesn't have a preferred direction. Wait a second, I need to correct my last statement because it isn't entirely true. Space can have a preferred direction, especially on Earth. When we throw something into the air, it doesn't move left or right, or forward or backward, it falls down. There is a preference towards the direction of the Earth's core because we are in a region where space-time is distorted by the mass of the Earth itself. The fact that Earth is right beneath our feet causes everything to move towards its core. However, if you were in a region of the universe far from any massive object, there wouldn't be a preferred direction, and you could move freely in any direction you wish. But this isn't true for time. You can't move backward in time, no matter where you are in a universe, not even at the edge of a black hole. Yet, like space, time is also distorted near a massive object, which is why we observe time dilation in GPS satellites. Another factor that makes time relative is the speed at which you are traveling. The faster you go, the slower time passes for you. This means two things can influence how we experience time: gravity and velocity. We can define direction in space, right, left, up, and down, but we still can't definitively say what time is. To make matters worse, it's almost as if each person has their own clock and experiences time differently. To illustrate how absurd this is, imagine that I spend a few hours near a black hole. For me, only a few hours might pass, but when I return to Earth, it could be decades later. People on Earth would have experienced time entirely differently than I did. But one thing remains true: no matter where you are in a universe or what your clock says, time always moves forward. But what defines this? What property or aspect of our universe dictates that time has an arrow pointing forward and prohibits it from going any other way? The answer is similar to how the Earth's mass gives a direction to space. We live in an influential something that gives direction to time, and that something is the Big Bang. We can say we live after an event that gave time its direction. When the Big Bang occurred, it introduced the concept of entropy, and that's when the idea of time having a direction made sense. Talking about time before the Big Bang is as meaningless as asking what is north of the North Pole. Some define entropy as a degree of disorder or randomness in a universe, while others might describe it as the number of possible arrangements of a system. Once a system reaches a state of higher entropy, it will never revert to a state of lower entropy. This is a fundamental law of the universe called the second law of thermodynamics, which states that the entropy of a system can never decrease. The universe itself is a massive system, and its entropy only increases. If I showed you two pictures, one of a broken egg and another of a whole egg, and asked which came first, you would almost always say the whole egg came first. This illustrates the concept of entropy. You've never seen a broken egg reassemble itself into a whole egg. So what does this have to do with the concept of time? Entropy defines the direction in which the universe moves. every system moves toward a state of higher entropy. Therefore, the arrow of time is defined in this way. It always points in the direction where entropy increases, never where it decreases. Even we are subject to entropy. We age because the chemical reactions in our bodies occur in ways that increase entropy. The second law of thermodynamics is so powerful that it underpins our physical understanding of the arrow of time. This answers part of the question. It explains why time only moves in one direction. However, we still don't fully understand what time itself is. One of the few physical theories that explicitly requires time as a tool is general relativity. However, general relativity has its limitations. It is not a fundamental theory of the universe. For a theory to be fundamental, it must explain all the concepts of the nature of the universe. And unfortunately, general relativity falls short. It cannot explain the singularities of black holes and fails to reconcile with quantum mechanics. One key issue where general relativity and quantum mechanics conflict is how they treat time. In quantum mechanics, processes can be reversible, and time is not considered a dimension in the same way. In contrast, in general relativity, time influences nearly everything, and you will always need to know how time is passing for each observer. Otherwise, the results won't make sense. This discrepancy suggests that general relativity might be an approximation of something even more fundamental that we have yet to discover. The quest to understand time continues, and it is one of the most profound mysteries in physics. The hope is that by uncovering a deeper theory, we might finally answer what time truly is and how it fundamentally operates in our universe. Some physicists suggest that time might be just an illusion and not a necessary component of the universe. Some even propose that time might not exist at all. However, the question of existence can become ambiguous. When we say something doesn't exist in physics, it doesn't mean it doesn't exist at all, but rather that it isn't necessary to describe a physical process. In this context, time might not be essential for describing the universe. It could be an illusion, masking something even more fundamental. Interestingly, there are studies exploring the idea that time is merely space in a dimension we cannot access. We live in a three-dimensional world, and time might be the distribution of matter in a way that, due to entropy making matter more disordered, gives the impression of being real. With this perspective, time could be an illusion because we lack access to this dimension. Yet, even without definitive answers to this hypothesis, it's fascinating to consider that time is only crucial in general relativity. In most other areas of physics, time is just a measure of the interval between two events, marked by something regular like the Earth's orbit around the Sun, which gives us a year. This question straddles the line between philosophy and physics. Time is so intrinsic to our lives that it's challenging to think of it as merely an illusion. Personally, I believe that these unanswered questions are what makes the universe so intriguing. But now, I leave you with a final question that I'd love to see you debate in the comments. When the universe reaches maximum entropy and thermal death occurs, what happens to time? Thank you very much, and I see you next time.